A2 Maths moments. Okay, so what I'd like you to do is just think about what we have set up here. We've got what we call a pivot, so some point just there, and a light rod coming out from that pivot. Now the best way to think about this is if you imagine it's flat on the floor and you've got this light rod, which could be thinking about as a meter ruler or some sort of stick that's coming out like that, and it's attached to the floor at one end. So it's free to move, okay? So it's free to move. Now if I attach a force to one end of it, maybe you could push it or you could kick that meter ruler, what would happen? It would clearly start to turn around that pivot. Okay, it would start to move around it. Now the turning effect around this pivot is what we call a moment. And hopefully you've seen that before. You've probably seen it in your science lessons at school. So we call it a moment. As you apply a force to that rod, it will move around that pivot point. Okay, you come across these clearly every single time you do something like open a door. You imagine when you open a door, think about where the door handle is. That's you applying a force and pushing open that door. The pivot of that door would be at the hinges where it's actually pivoting around. So it's exactly the same setup as you opening a door. So I'd like you to think about this question. Okay, what affects the magnitude, the size of that moment? Okay, so the bigger the moment, the faster that's going to move around that pivot. But what affects the size of that moment? That's what I'd like you to just think about. So just pause there, have a think about it. There's two things you should be thinking about. Okay, so clearly one of them is the size of the force, and we'll come back to that in a second. The other thing that's important is the distance from the pivot. Now, if you actually try doing this yourself, you could try opening your door. All right, so you could get up and you could try opening a door. Now, if you try opening the door from where the door handle is, that is a certain distance from the pivot. Okay, so you open it where the door handle is and the door should open really easily. You can push it where the door handle is, it should open really easily. Now, if you just put your hand really close to where you actually open the door, all right, really close, like that next to where the hinges are, you'd have to apply more force there for you to open the door. So the magnitude of the moment, if you applied the same force there on the door to there it would swing open, but here you would only just start to be able to move it. Okay, so the size of the moment is determined by the distance from the pivot. Okay, from the distance from the pivot. The other thing that clearly affects the size of the moment is the force, but you do need to be careful here. All right, you could apply a force straight up like that and you would get this nice moment spinning around a pivot. But if you just turn that force 90 degrees and had it facing out this way, in other words, the force was pulling away as if you're trying to pull it off the pivot itself, then what's going to happen is it's not going to turn at all. The same idea is if you imagine that you just open your door half wide, grab the door handles and try pulling the door outwards away from the hinges, it's not going to open. It's just going to stay still. All right, watch, not strong enough to pull it off the hinges. Okay, so you pull it outwards. It doesn't matter how much force you pull out in this direction, it's not going to turn around. So when you consider the force affecting the moment, it is what's called the perpendicular force. So when we talk about the force, we are only talking about the force that's perpendicular to the rod. Any force that's pulling in this sort of direction, although it will still turn around, if you try pushing your door open at that sort of funny angle, that would still open because you've still got some upward force. Right? But it's better to try pushing the door perpendicular to the door frame itself, right? To the door itself. Okay, grab your notebooks then, please. Just a quick note on what a moment is. It's a turning effect. Right, that could be your title. And then what I'm going to do is just give you the formula. So we can apply those two things that we just talked about. The force that you apply, the perpendicular force to the rod itself, but also the distance. Okay, so give yourself a moment, maybe pause there. Give yourself a moment. Yeah, very good. Okay, and got the formula down. So what I'm going to do, don't get this down in your notebook just yet, but sorry, get this bit down first of all. So the F is the force acting perpendicular to the rod, and D is the distance from the pivot to where the force is applied. Okay, so just pause there. Okay, so we've got this formula. What I'm going to do is I'm just going to try this formula on a simple example. So my simple example, there's your distance to your force. Simple example is this. So I've got a force, that's 20 newtons, okay, and D is my distance of 30 centimeters. So I'm going to use this formula. It's a really simple formula, isn't it? So F times the distance. All right, so what I'm going to do is do 20 newtons times 30 centimeters, and the answer comes out as 600. So I have a moment of 600. What I'd like you to do, please, is have a think, what is wrong with that? Okay, so what is wrong with that answer? That's what I'd like you to think about, please. So maybe pause there. Okay, so maybe if you've, like I said, you've done it on physics recently, or you've done it as science at school, you might know the answers. You may not. Okay, that a moment can be in either direction. So having it as clockwise or anti-clockwise is absolutely vital. We need to know which direction it's traveling. So it could be a moment of 600 clockwise or 600 anti-clockwise. So it's important to make sure that we define which direction it's traveling in. But the other thing is the units. Now, a moment is measured in what we call Newton meters. Now that means that if you're using 20 newtons, that's fine, but 30 centimeters was wrong. You need to be very careful with your units. So grab your notebooks out, stick that quick example down. You can put it down as an example. A force of 20 newtons is applied perpendicular to 30 centimeters, and just very quickly do the sketch because that's showing which direction the force is applied. So a really simple sketch. So just pause there, write down the question, do the quick sketch. Okay, so you've got that down in your notebooks. Let's make sure we get it right this time. So the first thing we need to be aware of is that moments can be measured in Newton meters, okay, and they can rotate both clockwise or anti-clockwise. So in this case, if we think about what's going to happen here, this D value, which is 30 centimeters, we're automatically going to change that to 0.3 meters. We're dealing with that as 0.3 meters. So don't get tricked out by the wrong units. The 20 newtons is going to be applying up here. So that to me is going to go anti-clockwise. Right? It's going the wrong way round. So we're talking about it being anti-clockwise. So the way we should have done it would be like this. The moment is 20 newtons times 0.3 meters. You don't need the newton and the meters in there as long as you got them in the correct units. So 20 times 0.3 would have been fine. And then once you've done that, you can write down the answer with the correct units. So 6 Newton meters anti-clockwise was the correct answer. And again, just pause there if you need to get that down in your notebook. Okay, so what I'd like you to do is just have a go at these 4 examples just here. So see if you can work out, as it's asking there, the moment of each of these light rods. And just to ask you, or if you're in class, I'll be asking you, what do we mean by a light rod? The word light. Now the word light just means that we don't have to take into account anything to do with weight of that rod. You can ignore the weight of that rod. Not very realistic, but that's what you can do. You can ignore the weight of it. Right, have a go at those. This is where you do need to pause, take your time with each of them, and see if you can work out the moments of each of them. Don't forget your unit, don't forget to define direction. Okay, so let's see how you got on with them. So this first one, what I should be considering is the formula is just force times distance from the pivot. It doesn't matter about this bit down here, as it says it's a light rod, so we can ignore that. So it's not got any weight to it at all. So if there's my pivot at A and there's my force, the distance from A to the force is going to be the difference between those two. So it's down to 3 meters. Meters is good. Force is in 16 newtons. So what's my total moment there? 16 times 3 meters. Notice you got, because the units are correct, so you can just not put any units on, equals 48 Newton meters, and it would go in a clockwise direction. Okay, so well done if you got that. Right, let's consider this one. If you use 12 newtons, then you would have been wrong. Okay, my hint to you is think about what's perpendicular to that rod. So if you're not sure, if I've given you a hint, pause again, have another go. Okay, so if I'm thinking what's perpendicular to this rod, going straight up will be 12, and it's not connected to that, because it's here, it will be sine. So 12 sine 30. Okay, going this direction is a 12 cos 30. So because we're ignoring anything going that way, we only care about the 12 sine 30 going straight up. All right, we can forget everything else. All right, they're not going to help with that moment at all. So 12 sine 30 goes straight up. Careful with 90 centimeters, 0.9 meters. Put both of those in. Grab your calculator, calculate it. Gets you 5.4 Newton meters in a clockwise direction. Still going in a clockwise direction. Okay, so well done if you got that. Right, so we go down to this one just here. So because this has got two forces, right, you've got the 18 newtons and you've got the 22. And because we're not sure which one we're going to be saying is positive, whether it's going to be anti-clockwise or clockwise, we don't know. All right. This one's got more force, but it's shorter distance. This one's got less force, but it's longer distance. So we're not 100% sure which direction it's going to be. We can decide which direction we want as positive. So we can look at it being in the anti-clockwise direction or the clockwise direction. We can just make that choice. All right. Doesn't matter which one you pick. Right, we'll talk about what happens at the end in a minute. So make a decision. All right, you make a decision whether you want to go down as positive. In other words, it'd be 22 times 5 minus 18 times 7, because that's in the opposite direction. Or you can go up as positive. Then it'd be 18 times 7, take away 5 times 22. It's totally up to you. To work out the total moments is putting those two things together. So I've opted for anti-clockwise to be my positive. So I've got 18 times 7 take away, because it's in the opposite direction, 22 times 5. What do I end up with? The answer, 16 Newton meters anti-clockwise. Now, if you pick the other direction as positive, you would have had minus 16 Newton meters clockwise. Right, and it's exactly the same answer. But what you probably find is because you got down to a minus, you would just change the answer. So if I did this the other way around, I got down to minus 16 Newton meters clockwise, I would then write underneath equals 16 Newton meters anti-clockwise. Right, you can change from positive to negative, you just change it from anti-clockwise to clockwise. You can flick it any way you like. There's absolutely nothing wrong with you writing minus 16 Newton meters clockwise. It's the same answer. Okay, so what if you got that? Again, giving a moment on this, considering the directions. So just pause again if you still need some more time with it. Okay, so the first thing you want to be doing on this question is just changing it so you're only concentrating on the forces perpendicular to the rod. So in this situation, we're looking at this one. Notice it's going to be not connected to the 70, so you could write it as 80 sine 70. Or you could write it as 80 cos 20. Either of those two would work. So go straight up would be 80 sine 70. All right, so I'll do that first of all. And then on this one, you've got to make a little bit of consideration because it's 120. I'm looking straight down. That would be 30 on this side. So you could write it as 50 cos 30 because it's connected to that 30. Right, what's important to notice then is both of these forces are acting, as it says here, in a clockwise direction. This one's pulling it that way, this one's pushing it this way. So both of them are pushing in this way. This one is going to spin in this direction faster and faster because both forces are pointing in the same direction. So that's important to notice that if I choose, I'm definitely going to choose this way clockwise as positive, then both of those are going to be positive. If this was pointing downwards, I have to consider that both of them are pointing in opposite directions. So always consider the direction when you choose whether it's going to be positive or negative. So positive, positive, both clockwise. So I'm going to get the 80 sine 70 times by 8 across and 50 cos 30 times by the 8 there. It's definitely going to spin clockwise. 948 Newton meters clockwise. We can see that all the units were correct. Meters, meters, newtons, newtons. Okay, so well done if you managed to get those. Just pause there. Okay, so you've got two exercises to have a look at. So I'd like you to go to exercise 1.1 and 1.2 and see whether you can do those questions. Okay, so let's look at this situation then. So we've got a light rod that's in equilibrium. All right, so I'll be asking, what does it mean to be in equilibrium? What does that mean? Okay, about the pivot A. Find the value of the force. So if we've still got a light rod, we don't need to worry about its weight. Again, if it's pinned on the floor and someone's pushing at 15 newtons, 2 meters away, so someone's trying to push that piece of wood just there, but then there's another force just here that's trying to push it anti-clockwise. So someone's trying to push it around clockwise and someone else is trying to push it around anti-clockwise. Now this is in equilibrium. So what that means is that both of those forces basically cancel each other out. They cancel each other out, and therefore this light rod is not moving. It has a moment of zero. Now you can have it so that it is continually moving at a constant rate. That's the same thing as being in equilibrium. But it is not, so all the forces acting on it basically cancel each other out. Now that helps us. If we know the moment is going to equal zero, then what that means is we can use this formula just here. So grab your notebooks and just make a note of this. If a rod is in equilibrium, then the sum of all the clockwise moments, so everything pushing clockwise, in this case the 15 times the 2, has got to be equal to all the anti-clockwise moments. They cancel each other out. So what I can do is I can use that fact to solve this question just here. Because what does that mean then? Just pause if you need more time. That in this case, we've got 15 times 2 equals F times 3. The clockwise ones must equal the anti-clockwise moments. And then it just means that it's very straightforward to solve. 15 times 2 is going to be 30. 30 divided by 3 gets you a force of 10 newtons. Okay? It's important just really to understand what we mean by equilibrium when it comes to moments. So pause there if you need more time. Okay, so let's make a bit more complicated situation then. I've got a horizontal uniform rod, okay, 10 meters, mass of 7 kilograms. So I've lost one of those key words that I've been using all the time, which was the word light. Because now we've got a situation where the actual rod itself has a mass. So I'm bringing that in. What I'd like you to do, first of all, then, please, is just have a go at what seems like a really straightforward question. If you wanted to put a pivot on there, all right, in other words, if you think of it as a seesaw, where would you put the pivot so that it rests in equilibrium? So a way of thinking about this is if you had like your 30 centimeter ruler in front of you, where would you put your finger so that you can balance that 30 centimeter ruler nice and neatly on your finger? Your finger will be the pivot. Where would you balance it? Okay, so the answer seems really logical and easy, but the question is this: why is it there? What's special about what's the wording? Okay, so hopefully you spotted the word uniform. Because it's a uniform rod, it means that its mass is spread out equally along the whole of its length. Okay, the mass is spread out equally along the whole of its length. What that means is this pivot here will be smack bang in the middle. All right, smack bang in the middle, which is why when you had your 30 centimeter ruler, you put your finger at 15 centimeters and rested it there, it should stay on your finger. All right, it should stay equally balanced. If you put it at 10 centimeters, the 20 centimeter end would drop down. Okay, there'll be a definite moment at that end. All right, from the mass pulling it down. Okay, so if you think about that 7 kilograms to spread all the way over there, and it rests literally on this point just here. Now, if you think about what force is applied at that point just there, going straight down, it will be the weight of this entire metal bar. All right, this entire uniform rod. So all 7 kilograms of this bar's length just here is resting on a single point. Now that's really helpful because if we want to look at something having a certain weight, it's like, where do you put the weight? Well, you put the weight mark at its centre of mass. And for a uniform rod, the centre of mass is is smack bang at the midpoint. So if this is 10 meters, I can measure 5 meters in, put an arrow going straight down. That is where the weight would be acting. That's 7G in this case. So in this case, it's 7G, but generally speaking, for a rod of mass M, the force mg acts at the centre of mass. So there, in this case, it would be 7G pulling straight down. Now, that, like I said, that's important because it gives you a force point. Okay, just there. Because if you imagine now I change the pivot to that point just there, and I want to look at the moment, what's happening? Because of the weight of this rod, we have 7Gs pulling down at a distance of 5 meters from that point. Okay, now I know if I put the pivot there, smack bang in the middle of the 5 meters, I would have 2.5 meters acting at 7G. So knowing where the center of mass is really important for when we're working out moments because it gives us that force point. And just be aware that you can get non-uniform rods. So a non-uniform rod means that there is more weight at one end than on the other. Or you might have a situation where you have a very thin section here, a very thick section here, so there's more mass, and then it tapers off. And the way of thinking about it, it could be something like a sword. You imagine you had a sword in front of you. You've got the heavy pommel end just here where you hold it, going down to a tapered point at the other end. Now the centre of mass of a sword is not going to be smack bang in the middle. In fact, it's down near the bottom end, which is why you say it's perfectly balanced. Right? Your pivot is down near the bottom end where your hand would be for a sword. And that is because it is non-uniform. It has more weight at the bottom end than it does at the point end. So we need to be aware of that, but it'd be very clear in your exam questions whether a rod is uniform or whether a rod is non-uniform. All right. Pause there if you need to take any more of those important notes. Okay, so sticking with your notebooks then, just write this question down. So a horizontal uniform rod, 6 meters, mass of 18 kilograms. A wire is attached to one end of the rod and holds it in equilibrium. The tension T acts vertically. So if you think about the rod being horizontal, it says it there, and the wire is attached to hold it vertically. The pivot A is a distance of 2.1 meters from the wire. Okay, draw the diagram, show the forces acting on the rod. Right, so what I'd like you to do then is grab the question down in your notebook, pause it, have a go at drawing it yourself. Okay, so what you might want to do is do it in a slightly different order to me. All right, depending on how you drew it, but let's have a look. Because there's a good chance you might have got it wrong. And if you actually look at your drawing, you might think, actually, I can see that that means it's going to be rotating round. So you might want to do some adjusting. My hint, before I give you the answer, my hint will be, do not forget that the wire can pull up or down. Okay, so let's have a look and see what you got then. So the first thing I would have drawn is some sort of rod, 6 meters, there we go. The mass is 18 kilograms. And don't forget that although that entire rod weighs 18 kilograms, the focal point, the center of mass, is going to be in the middle. So I can put 18G definitely pulling down towards the center of the earth. So that's what's happening. Okay. Now there's going to be a pivot on there, stopping it just dropping to the bottom, dropping to the floor. So there's got to be some sort of pivot in there. But there's also a wire. Now I've got my tension going in the correct direction. So if you put your tension in the opposite direction to that, okay, because you might have got it going straight up and thought, I can see what's happening here. This metal bar wants to drop down, so therefore my tension is going to hold it up. But the problem is the distance is 2.1 meters from the wire. So you might have wanted to put that in first and said, look, I know the wire comes from there. This is 2.1 meters. Now forget the tension in the wire. What would happen if I just had this rod balanced to that point? Well, what would happen is this bit here, because there's more of the bar on this side, or the rod on this side, it would start to move around this way. And also you can see it, can't you? Look, 18G, all right, is the force a certain distance away from here. So it wants to rotate round here. It wants to rotate clockwise. Now, if you had your tension going upwards, that's also going clockwise, in which case this entire bar would definitely spin around that pivot point. So what I've got to do is, because it's in equilibrium, right, it's in equilibrium, it's been held in equilibrium, is that tension force there has got to be in the opposite direction to that one. So this is pulling down clockwise, this tension is pulling down anti-clockwise. And if you'd accidentally put it going straight up, no problem, you can sort it now and have it go straight down. Okay, so what have I got then? Well, I've got the tension pulling there, and I've got the weight pulling there, and these two kind of cancel each other out. So if I work out the distance from the pivot to that point first of all as well, I know the whole lot's going to be 3 meters, so I am going to be dealing with about a distance of 0.9. So I've got those two bits of information, and now I'm sorted, aren't I? T times 2.1, 18 times 0.9, 18 times gravity times 0.9. Be careful not to think of the weight, not the mass. So it's in equilibrium, so therefore the anti-clockwise is going to be the T times 2.1, and that's going to equal 18G times 0.9, which is where you're going to get a tension of 75.6 newtons. All right, we're not looking for the moment in this because, of course, it's in equilibrium. The moment's equals 0. All right, so you're looking for the force due to tension. Okay, so well done if you managed to get that. Okay, so pause there until you've got what you need. Right, so I'll just put both of those forces on my diagram, and I know it's in equilibrium. What I'd like you to do is this, please. Is I know that the rod, like I said, is in equilibrium. What are the forces are acting on the rod? Okay, so what are the forces are acting on the rod? Now, the other force that's acting on the rod is the pivot itself. Because if the pivot wasn't acting, if there wasn't another force acting on it, and these two were just pulling straight down towards the centre of the Earth, the reason why it's not moving is because this pivot here is pushing back up. And it's pushing back up with a normal reaction force. The same as if you had something just sat on the ground. The ground pushes up with a normal reaction force. And what you need to be aware of is that the actual pivot itself will push up with the same forces that are pulling straight down. So you could look at it as a normal mechanics model there. Okay, so what's pulling straight down? Those two forces. But the situation is that it's not falling through the pivot and it's not flying up off the top of the board. So therefore, these two must be equal. So in this case, what is the value of R? It's going to be both of those two added together. So therefore, your R value will be 252 newtons. Now, there's a reason why I've put that on there. One, you need to be aware of that. Okay, you need to be aware because you have to look at the bigger picture. Okay, and you have the same situation with the pulleys that you've done previously in mechanics as well. When you imagine you've got a pulley system and you have I'll just get the right pen. You've got a pulley like that, and you've got a force pulling down this side and a force pulling down this side. Now those two are both exerting a force going downwards, so therefore the pulley has to have a force pulling upwards. Okay, so you've seen the same sort of situation there. Although you can do all the maths with these two, all right, to do with sort of resolving forces and things like that, you've also got to be aware of the bigger picture. All right, what forces are acting on that pulley? The two that are pulling straight down. What forces are acting on the pivot? The two forces pulling straight down. All right, so just be aware of the bigger picture as well. Okay. And what I'd like you to do is take the moments at these 3 different points. So we've got the point B. So imagine that was where my pivot was. All right, or that's where I want to take the moment. It's not about the pivot. I apologize for using that word. It's not the pivot. It's taking the moment at that point. So imagine I took the moment at B. All right, think about all the forces, different distances from B. What is the moment from C and what is the moment from D? And this is escaping the idea that where you're taking the moment from has to be the pivot. Okay, it's quite common that you do that, but it doesn't have to be. All right, right, that's what I'd like you to do, please. Work out the moment from each of those points. So pause it there and have a go. Okay, so if we took it from B, then what we notice is we've got two forces there. We can ignore the 75.6 because that is actually acting with a distance of 0 from B. It's actually acting on the B point. So I can ignore that completely. What have I got then? Well, I've got this 252 newtons, which was acting from the pivot, and that's pushing up a distance of 2.1. I've also got, acting from this point, 3 meters away, C pulling straight down with 176.4. Now I've decided that up is my positive, so therefore that bit is positive just there. Okay, just change the pointer. So that bit is my positive just there, minus that bit pulling down, which is my negative. And what do I find? The moments at the point B are equal to 0. Okay, they're definitely going to be equal to 0. Right, if you understand what to do now, have a go at C and D. Okay, so I'm taking my point from C. Now what's important about this bit is now I can ignore this value. Okay, even if I didn't know what it was, I could ignore it completely. All right, because there's no distance active from C. You being able to choose a pivot means that you can actually ignore certain values. So I've decided to do it. C means I can ignore the 176.4. I've then got the entire distance of 75.6 times 3. All right, and I've taken that as my positive, so going positive, whereas this 252 times 0.9 is my negative, so that's my negative value just there. What happens when I put those two in? Lo and behold, I get 0. So at both of those points, just there and there, and I've taken the pivot, I got 0. You also got it there, of course, as well, when we did the pivot at the actual pivot point, pivot A. So I can actually got 3 values now, and they all come up as 0. Right, no surprises on D then. But what's important about D is there's actually 3 forces. One pulling there, one a distance of 3.9, which is pulling straight up, and one a distance of 6, the other end of the bar, pushing straight down with 75.6. Okay, so I've got those 3 forces. Make sure you get the directions right on this one. So I've decided that down is positive, so that's down would be anti-clockwise about D. This one is positive as well, so 176.4 times 3. But this one is pulling clockwise, so that's why it's negative. And what do I get? No surprises, 0. It didn't matter where I took my pivot point or my moment at a point, it's always going to be equal to 0. Right, so make sure you've got that down in your notebook then. If you've got a rigid body in equilibrium, then the moments at any point along that line, along that rigid rod, okay, along that body would be equal to 0. It doesn't matter where you took it. Now that's important. And the reason why it's important is if you have this situation. Imagine I didn't know these two results. I didn't know that one and I didn't know that one. Okay, I call that X and I call that Y. I can choose where to take the moment from. Now, if I decided to do it there, what would happen is I could ignore this unknown here, this unknown X value. So by taking it there, I can ignore the X, and therefore I could work out what Y equals because I can ignore the X and work out Y. Then, of course, once I've done that, I can take another moment anywhere I like then, do it there, and I can ignore the Y value and calculate the X. So knowing having two unknowns is not going to cause you any problems in this situation because you can choose where to take the moment. But of course, you could also take any 2 points and have simultaneous equations. That would work just as well. Okay, so either choosing the cancelling out one or just choosing any 2 points and having simultaneous equations. Both methods would work as long as you understand you could take moments anywhere you like. So I'll pause there, give you a chance to get down what you need. Might be worth just making a note in there that, so to explain what that means is if you chose B, you can ignore the 75.6, and if you chose C, you can ignore the 176.4. You could choose to ignore values by taking the moments at them points. Okay, so I've got a uniform rod, mass M rests on 2 points A and B. And I've got this situation. The 2 points, A and B, exert a normal reaction force, don't they? Both of them. So the weight is coming on. Yes, this sticks out a bit longer over here, and we'll talk a bit about what that means. But basically, I've got these 2 points just here, and they have a normal reaction force. Just there, just there. Right? Now, they're not very well spaced out, but they're enough spaced out so it doesn't have any rotation. Okay? So because the centre of mass will be somewhere here. Now, this is the situation we're looking at. A person is standing at that far end of the rods. Right, so they're quite big. And what he's going to do is he's going to walk from one side of that rod to the other. Okay, he's going to walk across there. And what I'd like you to do is consider what happens to the normal reaction force RA and RB as he moves. So as he's moving across, okay, what's happening to the normal contact force at RA? And what's happening to the normal contact force at RB? So just have a think about that. I'll just shut up. Okay, so now it's past RB, but what about the normal contact force at RA? What's happening to it? Okay, so he gets to the other end of the rod. And if he weighed a certain amount, then you could be considering what's going to happen. All right, what's going to happen as he continues? Let's say that rod goes on forever. He continues walking to the end of that rod. What's going to happen at some point? Okay, now we know, or hopefully you figured out, that as he walked past RA, all right, so he started on this side, he walked past A, the pivot point A. The moment he walked past A and started to walk towards B, this normal reaction force here is starting to reduce. It needs to be quite strong to start with because the man is standing directly above it. Okay, but as he walks along and gets to B, the value of RA is starting to decrease because B is taking more of the mass. And as he goes past RB, now still carrying on, more of his mass is affecting B, less is affecting A. So the next question is this. We know that as the person walks past A and walks towards B, RA is decreasing, right? So I'm telling you that RA is decreasing. The question is, will RA ever decrease to 0? What do you think? Will that ever go to 0? Okay, so hopefully you've paused and had to think of it. And the answer is yes, it will go to 0. When you think about what's actually going to happen, at some point, that man is going to either walk far enough or weigh enough that it's going to rotate this bar about B. It's going to come down and hit the floor just there. At that point where it's about to start rotating around B, because at the moment, if I took that as my pivot, I can see that the man pulling down in this direction, and I've got a force pushing up, which is the weight of the rods. I've also got this force pushing up here. So there's lots of things going on, but it's not moving. It's still in equilibrium. But at some point, that man's mass is going to overcome the mass of the rod that's pushing up here somewhere, and therefore it's going to rotate. Now, if it rotates around B. It doesn't rotate around A, it rotates around B. Now, at A, it'll just sort of pull off A. All right, imagine just past equilibrium. It's going to come off A altogether. Now, at that point, it doesn't even know A's there. All right, A is not exerting any force on it at all. In fact, the only force acting on it when it's about to rotate is at the point where the pivot is. At the point where the pivot is, any other normal contact forces, in this case RA, can be ignored. And that's the important fact you need to get in your notebook. When a rod is at the point of turning, and yes, the examiner could be using those sorts of words, when it's about to turn, about a pivot, you can ignore other reaction forces. Now that's really helpful because if in this situation, it means you cancel out this unknown quantity just here. The only things you've got to work with is the centre of mass, figure out that one. That's going to be a force acting straight up there. And then also the mass of the person and RB. You can ignore RA altogether because it's just about to rotate off it. Okay, so just in your notebooks, get down what you need, pause if you need more time. Okay, so what I'd like you to do is have a go at the last two sections on moments, on those two exercises, which are to do with equilibrium and points where it's about to rotate. Okay, so we're going to look at one last section then. So everything we dealt with so far to do with moments has been to do with rods, right? Like a seesaw, like a flat surface, right? Or a straight line. Now what we're looking at now is extending that single line into a 2D surface. And in fact, we're only going to be dealing with rectangles. You can have all sorts of 2D objects, but you guys are only going to have to worry about rectangles. Now, just want to mention the word lamina. So a lamina is a 2D object, right, like I was just talking about, just a rectangle that has no thickness. So the best way to think about this is like a piece of paper. I know a piece of paper has a thickness, but on a whole, we look at that as just a flat 2D object. Its thickness is so small, we don't need to consider it. And the other thing we might have use the word is like a laminated surface, right, or a laminated piece of wood. What that means is that like you have a very thin surface to it. A laminated floor would have a very thin picture of a piece of wood that has no thickness at all. Okay, so why is that important then? Well, that's what we're going to be moving on to now. We've dealt with rods and pivots on rods, but what about if you had like a piece of paper? If you imagine you've got a piece of paper and you held it in one of the corners, that piece of paper starts to rotate round. If you held it in the middle, then it doesn't rotate round because that's talking about where its centre of mass is. But if you have a piece of paper and you hold it in a corner, just lightly, not too firmly so it can't move, just lightly, that piece of paper will naturally start to rotate around. So it has something to do with moments. Okay, so that's why we're talking about centre of mass though. Let's just talk about that first of all. So the centre of mass for a lamina, you can find it by using the lines of symmetry. Right, now this is more important for more complicated laminas, more complicated 2D objects, but it's worth showing you for rectangles. So you imagine you've got a rectangle like that. Where would the centre of mass be? It's going to be somewhere in the middle, and the way you could find it is by putting in the two lines of symmetry. So it's got a line of symmetry there, it's got a line of symmetry there. That bit just there is where the centre of mass is going to be. Okay, and that technique can work for anything, any shape. You can see this if you had your piece of paper, like we had earlier. If you fold it in half and then fold it in half again, and then unravel it, unfold it, where those two lines cross, if you put your fingers in there and held that piece of paper, it will not rotate. Whereas anywhere else, as long as you're not holding it too tightly, it should rotate. Now it's quite interesting, the further you are away from that centre of mass, the more that piece of paper is likely to rotate. So you held that piece of paper in one of its corners, it rotates quite openly. If you had your fingers very close to the centre of mass, it may not even rotate at all because you've got your distance from the centre of mass is too small. So it still has that same idea of what we were discussing with rods, that to do with the distance from the centre of mass, to do with a distance from the pivot point. Okay, so what we're going to do is we're going to look at these 4 examples and talk about how to actually go about solving them. Your exam is not going to get any more complicated than these types of examples. So let's have a look for what I'd like you to do is have a go yourselves. Just consider what the problem is, see if you can solve any of them yourself. If not, we'll work through them all together. Okay, or you might want to just do the first one with me and then you can have a go at the others yourself. Okay, so I've got this situation just here. This is my laminated surface just here, my lamina. There's my pivot point, and I've got a force acting at 16 newtons pulling straight down. Now just have a think about what's going to happen just like in that situation. Now we know, right, that as long as there's no friction acting on it, that this is going to mean that the whole piece of paper, that whole rectangle, is going to start rotating round. And in fact, the question is this: did it make any difference that it's a 2D object? If it was just a rod going down like that with 16 newtons, would you have got exactly the same effect? All right? Did it make any difference about that? Did it make any difference if that was 5 meters high or 20 meters high and you applied 16 newtons down like that? Would it make any difference? Now the answer is no. It makes no difference at all about the height of this 3 meters doesn't make any difference. And in fact, that does not play a part in it at all. The only things that play a part is the point where you've got your force, and that point could be anywhere along there. All right, so the point where we've got the force and the perpendicular distance from the pivot. Now in this case, it's 5 meters away and it's down at 16 newtons. That 3 meters doesn't come into it at all. Then once you've reduced it down to that sort of problem, now we can use our moments the same as we did before. What's the answer? 16 times 5, so it's going to be 80 newton meters clockwise. And notice I can get rid of my lamina completely. Now you've got the idea of what to do with that, you might want to pause and have a go at the others. Okay, should we have a look at this one? This one's interesting. I've got the pivot there, the lamina's pointing out that, and I've got a force of 70 newtons pulling in that direction. What's going to happen? Okay, especially if you think of this as flat on the floor. All right, you've got a piece of paper flat on the floor, you stuck your finger where A is, all right? It's not going to rotate anywhere because it's flat on the floor. Before it rotated because it was falling under gravity. But now, if it's on the floor and you put your finger where A is on that piece of paper, it's not going to move. Now, what I'd like to do is grab the opposite corner to it and pull it, not like that one, which was 16 newtons downwards, but pull it with a force pulling outwards. So you've got your finger on this end and you're pulling it from the other corner outwards. What happens to that piece of paper? Well, if you did it right and you put your finger there and you try pulling this direction, nothing is going to happen to that piece of paper. There, it rotated because you're pulling it down. But here, because you're pulling perpendicular to the piece of paper just there, sorry, parallel to it, therefore, it's not going to move at all. What's the moment in that situation? 0. All right, that has a 0 moment. There's no forces acting perpendicular to the pivot. No forces acting up and down in any of the directions. So the moment is going to be 0. Okay, have a think about this one. Again, you might want to pause and think about yourself. Okay then. So in this situation, be very careful which one's which. Okay, the 11 newtons is definitely pulling up. So you're pulling up with 11 newtons there and you're pulling out with 15 newtons here. I don't blame you for thinking, oh, 15 newtons, that's parallel. So therefore you ignore it. 11 newtons is parallel, so therefore you ignore it. But be careful. That 11 newtons there, just because it looks like it's on this corner, actually applies all the way along that line. So in fact, you do have a line there, and this 11 newtons is perpendicular to it. So this 11 newtons is going to affect it. This 15 newtons, although it looks like it's starting there, it doesn't necessarily have to. It can be right over here. So this is 15 newtons, which is 3 meters away from this line. So in fact, we have these two situations. 15 newtons, 3 meters away from that pivot. And so I could put that on, and it's pulling clockwise. So therefore, I've got a moment of 15 times 3. The other force to consider was the 11 newtons at 5 meters, and that is pulling anti-clockwise. Now I've decided that clockwise is my positive, so therefore this one will be my negative. 15 times 3, take away 11 times 5. I get minus 10 newton meters clockwise, or 10 newton meters anti-clockwise. Notice that I chose badly in that case because I chose one with negative. It doesn't matter. It's still correct, but 10 newton meters anti-clockwise is preferable because you don't have any negatives. Okay, last one. Lamina has a weight of 9 newtons. Okay, now if it's got a weight, we have to do exactly the same as what we did with rods. We think about where the centre of mass is. Now the centre of mass is smack bang in the middle there. And that point just there is pulling down with 9 newtons. So there we go. There's the centre of mass. There's 9 newtons pulling straight down. Notice it's not its mass. I didn't say it's mass then, I didn't mean to. It's weight of 9 newtons. Okay, it's mass you don't need to worry about in this case. So it's got a force of 9 newtons pulling straight down due to its weight. All right, so I can definitely put those in. And now I can consider where that's pointing. Now, if you look at where I've dropped it there, you can see that this 9 newtons is actually acting perpendicular to this line just here. So I need this distance from there to there to be able to calculate it. So it's got a distance of 2.5 and it's going down at 9 Newton meters. So it's got a moment of 9 times 2.5. Okay, it has nothing to do with this 3 at all. If you're thinking it's 1.5, yes it is, but then it's not pulling in this direction with 1.5. So that's the only force acting on it. Therefore, it would start to rotate. That's the same situation as that piece of paper we just held in the corner of 22.5 Newton meters clockwise. Okay, in your textbook, there's lots and lots of extra questions which you do not need to worry about. The only thing you need to do is question 1 on page 459. You don't need to do any more than that part of that exercise. Okay, and that's all of the mechanics complete.